guys, welcome to this video where we're going to have a look at integrating trig functions. Okay, so we're going to start off by getting straight into having a look at a few examples and have a look at a very brief set of notes on the left here. And the first example we're going to have a look at is how to integrate the sine function here. So what's on the left here? Well, this is essentially just a copy of what's on page 174 of your workbook. And what we've got here is essentially a table which is the reverse of the differentiation functions that we looked at for trig functions earlier. So previously we've seen, for example, if we've got a sine function and we derive it, we saw that that was equal to the cosine function. So it sort of stands to reason then that since integration is the reverse process of differentiation, that when we integrate the cosine function we should get the sine function, and of course with our constant of integration. So this is essentially just a table of those antiderivatives. So the integral of cosine is sine, the integral of sine is negative cosine, and so on. Okay, so let's have a look and see how we can apply that. Now what we're trying to do here once again is not only use the fact that the integral of a sine function is negative cosine, but we've got here more than just a basic sine function. We've got essentially a composite function here. So we have to reverse the chain rule process. And what we're going to do for a number of these early examples is to have a look at doing this by essentially a try and improve method. So how does that work? Well, let's do this one through then. So we can see here that the integral of sine is negative cosine. So I'm going to try, say, well, maybe the answer is negative cosine 5x plus 3. And we're going to check that by deriving. So if I take this function here and derive, we're going to get the derivative of cosine is negative sine, so the derivative of negative cosine will be positive sine, and 5x plus 3. But since we're deriving, we're using the chain rule, so we derive by what's inside here. Remember, here we are checking by deriving what we think might be our answer, and this comes out to 5 sine 5x plus 3. Okay, well, as we can see, we're out. This is pretty close to this, but we're out by a factor of 5. So let's improve that by compensating for that factor of 5, and we got that factor of 5 because we multiplied by 5 here. So maybe an improved answer would be negative 1/5 cosine 5x plus 3 plus our constant, and let's check that once again by deriving this better answer. So the derivative of negative cosine, remember, is positive sine. So this will be positive sine, or 1/5 sine 5x plus 3 times our 5, and the 1/5 and the 5 cancel, and we've got back to our original function, which is what we're after. Remember, what we're doing here is deriving to check to see if this is now our actual answer, and yes it is. Okay, it actually works because we can prove that by deriving it and getting back to our original function. Okay, so our final answer then, okay, this negative 1/5 cos 5x plus 3 plus c. Now we'll have a look later and see if we can basically speed this process up, but let's have a look at another example or two first. Okay, so let's take something which looks a little weird when you first try and integrate it. Let's take something involving the sec squared here. So let's say we had to integrate 3 sec squared of 7x with respect to x. Okay, now according to this table the integral should be tan, so let's try. Possible answer: 3 tan 7x plus c. Let's check that. Once again, our check is deriving this, and the derivative of tan was sec squared, so we're going to get 3 sec squared 7x, but then the chain rule is applied, so we get times 7. So once again we're out by a factor of 7 by the looks of it, so this becomes 21 sec squared 7x, and we wanted a 3 in front, not a 21, so we need to compensate for this times 7 factor. So let's improve our answer. How do we compensate for this times 7? Well, but by dividing by 7, timesing this by 1/7 in other words. So we're going to get 3/7 tan 7x plus c. That's a tan there. I'm sure you can imagine that's a tan. Okay, and let's check that one. Okay, so let's derive this to check. So it'd be 3/7 sec squared 7x times 7. Okay, and the 7th there divided by 7 and the times 7 cancel, and we get 3 sec squared 7x, which is great because that's what our original function was. Once again, remember, we're simply doing this check to show to see if this here is the correct answer, and we do that by deriving it, and we have got our original function back. So that's great. So we can say that the answer is indeed our 3/7 tan 7x plus c. Okay, let's do one more, and then I think we'll try and see if there's a shortcut to this. Okay, so let's add a new blank page in, and let's call this example 3. Okay, let's take one of these ones which is in your workbook. I'm going to take a look at question number 42. Okay, so this one looks pretty daunting to begin with. It's 2 cosec 3x plus 1 times the cotan of 3x plus 1 with respect to x. And think, well, how the heck am I meant to do that? Well, let's just go back to that table. Cosec x cotan x is negative cosec x, that's the integral, and this are the same, so can we simply say that maybe the answer then is negative 2 cosec, what was it again? Cosec, yeah, not cosec squared. Okay, so cosec 3x plus 1 plus a constant. Okay, well, let's check again. Remember, this is our try here. Okay, and if I derive this cosec function, it should be negative the derivative of cosec. If I go back to our table in the book, what was the derivative of cosec? Negative cosec cotan. So this is when you derive it, should become positive then to cosec 3x plus 1 times cotan 3x plus 1, and then the chain rule kicks in as well, times 3. Okay, so we're going to end up with a 6 in front and we want a 2. So we're out by a factor of 3. So we need to compensate for that by dividing by 3 or multiplying by 1/3. Okay, so let's try a better answer then. Okay, so compensating for that factor of times 3, let's say negative 2/3 cosec 3x plus 1 plus a constant, and let's check it. Now the derivative again of cosec is negative cosec x cotan x, so this is going to become the negative of negative 2/3, which will become positive, of course. Cosec 3x plus 1 times cotan 3x plus 1 and times the 3 from the chain rule. The positive 2/3 times 3 becomes positive 2. Cosec 3x plus 1 times cotan 3x plus 1, and that's what our original function was. So yes, this does seem to be the correct answer. Okay, and so our correct answer was negative 2/3 cosec 3x plus 1 plus c. Okay, well, you might have noticed that every single time we have something here, or in this case 2 of them, that eventually when you check our original answer or try is going to produce a factor of, well, whatever is in front of this x here. So I'm talking about a situation where we've got, okay, the integral, let's take something which is, a little bit more straightforward than this previous one. Let's say it was the cosine of 7x plus 10. I reckon I know that the factor that's going to put our original try out is going to be 7, because when we apply the chain rule we're going to end up multiplying by 7. So I think that instead of doing try, derive, try, check, try again, check again, I reckon I'm going to go straight to saying, well, I reckon the answer is going to be, well, the integral of a cosine function is sine. I reckon it's going to be 1/7 sine 7x plus 10 plus c, and I'm going to put that compensating 1/7 there for a start, and then I'm just going to check. Okay, so the derivative of this would be 1/7 cosine 7x plus 10 times 7. Yeah, they certainly cancel, and we do get cosine 7x plus 10, which is our original function. So this is correct here. And what I would do in my working is perhaps set it out that way and make clear, perhaps not with a tick, which might be a little presumptuous if it was in the exam, and make clear that this is my answer. Okay, let's call that example number 4, and let's try one more. Once again, just trying to speed up the process using this more streamlined sort of approach here. Okay, so let's say we had the integral of negative 2/3 sine 1/2 x with respect to x, and that should have been up here too, of course. Okay, so what do we do here? Well, I reckon the integral of sine is negative cosine. The negative 2/3 with the negative cosine, I reckon that's going to be positive 2/3, and we're going to have we need to compensate for the times half. Well, how do we do that? How do we compensate for multiplying by a half? Okay, well, I reckon if the compensating thing would be to multiply by 2, or to divide by a half, which is equivalent to multiplying by 2. So I'm going to multiply by 2, and cosine 1/2 x plus c, and let's just tidy that up. 4/3 cosine 1/2 x plus c, I reckon, is the answer. Right, let's check. Okay, let's derive this. So 4/3, the derivative of cosine is negative sine of 1/2 x. Chain rule kicks in, so it times a half, and that simplifies to half times 4/3, that's going to be 4/6, which will be 2/3, and we've got a negative there, so yep, those constants all simplify down to negative 2/3. 4/3 times a half. Okay, that's 4/6, or you could have cancelled the common factor of 2, which gives you 2/3 either way. But we've got a negative here, so that's why it's going to be negative 2/3. Okay, so negative 2/3 sine 1/2 x, which is great because that's what I started with. Okay, so this must be the correct answer here then. So identify that as my answer. Okay, folks, that's really how we're going to attempt those trig function questions, and yep, I will put a couple of questions for you to do as well in this video that about now. Well guys, here are then a couple of problems that I'd like you to have a go at. Okay, so this first question should be appearing pretty soon, and here is the second question. Okay, good luck with that one as well.